Okay, testing 1, 2, 3. Let's quick check that everything is working correctly. Alright, and we're in. I guess with that, I won't delay and I'll get straight into it. Chapter 7, Introduction to Cryptography. Cryptography is the study of sending and receiving secret messages. The aim of cryptography is to send messages across a channel so that only the intended recipient of the message can read it. In addition, when a message is received, the recipient usually requires some assurance that the message is authentic. That is, that it has not been sent by someone who is trying to deceive the recipient. Modern cryptography is heavily dependent on abstract algebra and number theory. The message to be sent is called the plain text message. The disguised message is called the ciphertext. The plain text and the ciphertext are both written in an alphabet, consisting of letters or characters. Characters can include not only the familiar alphabetic characters A, B, all the way up to Z, and the lowercase a all the way up to lowercase c, but also digits, punctuation marks, and blanks. A crypto system, or cipher, has two parts. Encryption, the process of transforming a plain text message to a ciphertext message, and decryption, the reverse transformation of changing a ciphertext message into a plain text message. There are many different families of crypto systems, each distinguished by a particular encryption algorithm. Crypto systems in a specified cryptographic family are distinguished from one another by a parameter to the encryption function called a key. A classical crypto system has a single key, which must be kept secret, known only to the sender and the receiver of the message. If person A wishes to send secret messages to two different people B and C, and does not wish to have B understand C's message or vice versa, A must use two separate keys. So one crypto system is used for exchanging messages with B, and another is used for exchanging messages with C. Systems that use two separate keys, one for encoding and another for decoding, are called public key crypto systems. Since knowledge of the encoding key does not allow anyone to guess at the decoding key, the encoding key can be made public. A public key crypto system allows A and B to send messages to C using the same encoding key. Anyone is capable of encoding a message to be sent to C, but only C knows how to decode such a message. 7.1 Private Key Cryptography. In single or private key crypto systems, the same key is used for both encrypting and decrypting messages. To encrypt a plain text message, we apply to the message some function which is kept secret, say f. This function will yield an encrypted message. Given the encrypted form of the message, we can recover the original message by applying the inverse transformation f to the negative 1. The transformation f must be relatively easy to compute, as must f to the negative 1. However, f must be extremely difficult to guess from available examples of coded messages. Example 7.1. One of the first and most famous private key crypto systems was the shift code used by Julius Caesar. We first digitized the alphabet by letting a equals 00, b equals 01, all the way up to z equals 25. The encoding function will be f of p is equal to p plus 3 mod 26. That is, a goes to d, b goes to e, all the way up to z goes to c. The decoding function is then f to the negative 1 of p is equal to p minus 3 mod 26, which is equal to p plus 23 mod 26. Suppose we receive the encoded message DOJ HEUD. To decode this message, we first digitize it as 3, 1, 4, 9, 7, 4, 23. Next, we apply the inverse transformation to get 0, 11, 6, 4, 1, 17, 0, or algebra. Notice here that there's nothing special about either of the numbers 3 or 26. We could have used a larger alphabet or a different shift. Cryptanalysis is concerned with deciphering a received or intercepted message. Methods from probability and statistics are great aids in deciphering an encrypted message. For example, the frequency analysis of the characters appearing in the interpreted message often makes its decryption possible. Example 7.2. Suppose we receive a message that we know is encrypted by using a shift transformation on single letters of the 26-letter alphabet. To find out exactly what the shift transformation was, we must compute b in the equation f of p is equal to p plus b mod 26. We can do this using frequency analysis. The letter E equals 04 is the most commonly occurring letter in the English language. Suppose that S equals 18 is the most commonly occurring letter in the ciphertext. Then we have good reason to suspect that 18 is equal to 4 plus B mod 26, or B is equal to 14. Therefore, the most likely encrypting function is f of p is equal to p plus 14 mod 26, and the corresponding decrypting function is f to the negative 1 of p is equal to p plus 12 mod 26. It is now easy to determine whether or not our guess is correct. Simple shift codes are examples of monoalphabetic cryptosystems. In these ciphers, a character in the enciphered message represents exactly one character in the original message. Such cryptosystems are not very sophisticated and are quite easy to break. In fact, in a simple shift as described in example 7.1, there are only 26 possible keys. It would be quite easy to try them all rather than to use frequency analysis. Let us investigate a slightly more sophisticated cryptosystem. Suppose that the encoding function is given by f of p is equal to ap plus b mod 26. First, we need to find out when a decoding function f to the negative 1 exists. Such a decoding function exists when we can solve the equation c equals ap plus b mod 26 for p. By proposition 3.4, this is possible exactly when a has an inverse, or equivalently, when the greatest common divisor of a, 26, is equal to 1. This is because if the GCD of a and 26 is equal to 1, then AP will cycle through everything, and then this will just be a permutation on it by adding B to it. So we know that we'll have something that goes through every number uniquely mod 26. In this case, f to the negative 1 of p is equal to a to the negative 1 p minus a to the negative 1 b mod 26. Such a cryptosystem is called an affine cryptosystem. Example 7.3. Let us consider the affine cryptosystem f of p is equal to ap plus b mod 26. For this cryptosystem to work, we must choose an a in z mod 26 that is invertible. This is only possible if the greatest common divisor of a and 26 is equal to 1. Recognizing this fact, we will let a equal 5, since the greatest common divisor of 5 and 26 is equal to 1. It is easy to see that a to the negative 1 equals 21. Therefore, we can take our encryption function to be f of p is equal to 5p plus 3 mod 26. Thus, algebra is encoded as 3, 6, 7, 23, 8, 10, 3, or DGHXIKD. The decryption function will be f to the negative 1 of p equals 21p minus 21 times 3 mod 26, which is equal to 21p plus 15 mod 26. A cryptosystem would be more secure if a ciphertext letter could represent more than one plaintext letter. To give an example of this type of cryptosystem, called the polyalphabetic cryptosystem, we will generalize affine codes by using matrices. The idea works roughly the same as before. However, instead of encrypting one letter at a time, we will encrypt pairs of letters. We can store a pair of letters p1 and p2 in a vector p equals p1, p2. Now, let A be a 2x2 invertible. I will quick highlight this here. This is the same as the previous condition that we were able to find an inverse. Let A be a 2x2 invertible matrix with entries z mod 26. We can define an encoding function by f of p equals ap plus b, where b is a fixed column vector, and matrix operations are performed in z mod 26. The decoding function must be f to the negative 1 of p equals a to the negative 1 of p minus a to the negative 1 of b. Example 7.4. Suppose that we wish to encode the word help, H-E-L-P. The corresponding digit string is 7, 4, 11, 15. If a is equal to 3, 5, 1, and 2, then a to the negative 1 is equal to 2, 21, 25, 3. If b is equal to 2 to the t, then our message is encrypted as RRGR. The encrypted letter R represents more than one plaintext character. Frequency analysis can still be performed on polyalphabetic cryptosystem because we have a good understanding of how pairs of letters appear in the English language. The pair TH appears quite often. The pair QZ never appears. To avoid decryption by a third party, we must use a larger matrix than the one we used in example 7.4. Before I keep reading, let me make sure that it's working. Okay. 7.2. Public key cryptography. If traditional cryptosystems are used, anyone who knows enough to encode a message will also know enough to decode and intercept a message. In 1976, W. Diffie and M. Hellman proposed public key cryptography, which is based on the observation that the encryption and decryption procedures need not have the same key. This removes the requirement that the encoding key must be kept secret. The encoding function f must be relatively easy to compute, but f to the negative 1 must be extremely difficult to compute without some additional information, so that someone who knows only the encrypting function, or encrypting key, cannot find the decrypting key without prohibitive computation. It is interesting to note that to date, no system has been proposed that has been proven to be one way. That is, for any existing public key crypto system, it has never been shown to be computationally prohibitive to decode a message with only knowledge of the encoding key. The RSA crypto system. The RSA crypto system, introduced by R. Rivest, A. Shabir, and L. Adelman in 1978, is based on the difficulty of factoring large numbers. Though it is not a difficult task to find two large random primes and multiply them together, factoring a 150-digit number that is the product of two large primes would take 100 million computers operating at 10 million instructions per second, about 50 million years of under the fastest algorithm available in the early 1990s. Although the algorithms have improved, factoring a number that is a product of two large primes is still computationally prohibitive. The RSA crypto system works as follows. Wait, before I do this, I'm going to take a quick drink of water. Alright. The RSA crypto system works as follows. Suppose that we choose two random 150-digit prime numbers p and q. Next, we compute the product n equals pq, and also compute phi of m is equal to p minus 1 q minus 1, where phi is Euler's phi function. Now, we start choosing random integers e until we find one that is relatively prime to m. That is, we choose e such that the greatest common divisor of e and m is equal to 1. Using the Euclidean algorithm, we can find a number d such that de is congruent to 1 mod m. The numbers n and e are made public. Suppose now that a person B, Bob, wishes to send person A, Alice, a message over a public line. Since e and n are known to everyone, anyone can encode messages. Bob first digitizes the message according to some scheme. Say, our standard scheme a equals 0, 0, b equals 0, 2, up to z equals 25. If necessary, he will break the message into pieces such that each piece is a positive integer less than n. Suppose x is one of the pieces. Bob forms the number y equals x to the e mod n and sends y to Alice. For Alice to recover x, she need only compute x equals y to the d mod n. Only Alice knows d. Example 7.5. Before expanding the theory behind the RSA crypto system or attempting to use large integers, we will use some small integers just to see that the system does indeed work. Suppose that we wish to send some messages, which when digitized is 25. Let p equal 23 and q equals 29. Then n equals pq equals 667, and phi of n is equal to m is equal to p minus 1, q minus 1 is equal to 616. We can let e equals 487, since the greatest common divisor of 616 at 487 is equal to 1. The encoded message to be is computed to be 25, the message we wanted to compute, to the 487, mod 667 is equal to 169. The computation can be reasonably done by using the method of repeated squares as described in Chapter 4. Using the Euclidean algorithm, we determine that 191e is equal to 1 plus 151m. Therefore, the decrypting key is nd is equal to 667, 191. We can recover the original message by calculating 169 to the 191 mod 667 equals 25. Now, let us examine why the RSA crypto system works. We know that de is congruent to 1 mod m. Hence, there exists a k such that de is equal to km plus 1 is equal to k phi of n plus 1. There are two cases to consider. In the first case, assume that the greatest common divisor of x and n is equal to 1. Then, by theorem 6.18, y to the d is equal to x to the e to the d is equal to x to the de is equal to x to the kn plus 1 is equal to x to the phi of n to the k of x is equal to 1 to the k x equals x mod n. So, we see that Alice recovers the original message x when she computes y to the d mod n. For the other case, assume that the greatest common divisor of x and n is not equal to 1. Since n equals pq and x is less than n, we know that x is a multiple of p or a multiple of q, but not both. We will describe the first possibility only, since the second is entirely similar. There is then an integer r, with r less than q and x is equal to rp. Note that we have the greatest common divisor of x and q is equal to 1, and that m is equal to phi of n is equal to p minus 1, q minus 1 is equal to phi of p, phi of q. Then, using theorem 6.18 but now mod q, we have that x to the km is equal to x to the k, phi of p, phi of q, is equal to x to the phi of q, k phi of p, is equal to the 1, is equal to 1, k phi of p, is equal to 1 mod q. So there is an integer t such that x to the km is equal to 1 plus tq. Thus, Alice also recovers the message in this case, with y to the d is equal to the k to the m plus 1, is equal to the k to the m x, is equal to 1 plus tq x, is equal to x plus tq rp, is equal to x plus trn, is equal to x mod n. We can now ask how one would go about breaking the RSA crypto system. To find d given n and e, we simply need to factor n and solve for d by using the Euclidean algorithm. If we had known that 667 is equal to 23 times 29 in example 7.5, we could have recovered d. Message verification. There is a problem of message verification in public key crypto systems. Since the encoding key is public knowledge, anyone has the ability to send an encoded message. If Alice receives a message from Bob, she would like to be able to verify that it was Bob who actually sent the message. Suppose that Bob's encrypting key is n prime, e prime, and his decrypting key is n prime, d prime. Also, suppose that Alice's encrypting key is n, e, and her decrypting key is n, d. Since encryption keys are public information, they can exchange coded messages at their convenience. Bob wishes to assure that the message he is sending is authentic. Before Bob sends the message x to Alice, he decrypts x with his own key. X prime is equal to x d prime equals mod n prime. Anyone can change x prime back to x just by encryption, but only Bob has the ability to form x prime. Now, Bob encrypts x prime with Alice's encryption key to form y prime is equal to x prime to the e mod n, a message that only Alice can decode. Alice decodes the message and then encodes the result with Bob's key to read the original message, a message that could have only been sent by Bob. Historical note. Encrypting secret messages go as far back as ancient Greece and Rome. As we know, Julius Caesar used a simple shift code to send and receive messages. However, the formal study of encoding and decoding messages probably began with the Arabs in the 1400s. In the 15th and 16th centuries, mathematicians such as Alberti and Vieta discovered that monoalphabetic cryptosystems offered no real security. In the 1800s, F.W. Kasiski established methods for breaking ciphers in which ciphertext letters can represent more than one plaintext letter, if the same key was used several times. This discovery led to the use of cryptosystems with keys that were used only a single time. Cryptography was placed on firm mathematical foundations by people such as W. Friedman and L. Hill in the early parts of the 20th century. The period after World War I saw the development of special-purpose machines for encrypting and decrypting messages, and mathematicians were very active in cryptography during World War II. Efforts to penetrate the cryptosystems of the Axis nations were organized in England and in the United States by such notable mathematicians as Alan Turing and A. Albert. The Allies gained a tremendous advantage in World War II by breaking the ciphers produced by the German Enigma machine and the Japanese Purple ciphers. By the 1970s, interest in commercial cryptography had begun to take hold. There was a growing need to protect banking transactions, computer data, and electronic mail. In the early 1970s, IBM developed and implemented Lucifer, the forerunner of the National Bureau of Standards Data Encryption Standard, or the DES. The concept of a public key crypto system, due to Diffie and Hellman, is very recent, as in 1976 recent. It was further developed by Rivest, Shamir, and Adelman with the RSA crypto system in 1978. It is not known how secure any of these systems are. The trapdoor knapsack crypto system, developed by Merkel and Hellman, had been broken. It is still an open question whether or not RSA systems can be broken. In 1991, RSA Laboratories published a list of semi-primes, numbers with exactly 2 prime factors, with a cash prize for whoever was able to provide a factorization. Although the challenge ended in 2007, many of the numbers have still not yet been factored. There's been a great deal of controversy about research in cryptography and cryptography itself. In 1929, when Henry Stimson, Secretary of State under Herbert Hoover, dismissed the Black Chamber, or the state's department's cryptography divisions, on the ethical grounds that gentlemen do not read each other's mail during Henry Stimson dismissed the Black Chamber on the ethical grounds that gentlemen do not read each other's mail. During the last 2 decades of the 20th century, the National Security Agency wanted to keep information about cryptography secret, whereas the academic community fought for the right to publish basic research. Currently, research in mathematical cryptography and computational number theory is very active, and mathematicians are free to publish their results in these areas. And not worrying about Sage. So the reading questions. Okay. Use the Euler phi function. Nope. Okay. Explain the mathematical basis for saying encrypting a message using an RSA public key is very simple computationally, while decrypting a communication without the private key is very hard computationally. It mainly comes down to the fact that the public key is listed as public knowledge for one to compute with, so you just need to apply a simple formula with that public key in order to encrypt the message. But to decrypt the message, you need a very specific knowledge of the private key that only you have. And that requires a difficult problem of factorizing primes if you want to reverse engineer the process. Explain how an RSA message encoding differs from message verification. RSA encoding is a simple one-way function, while message verification requires a comparison of 2 different private keys in a mathematically consistent way to actually verify. Explain how one could be justified in saying that Diffie and Hellman's proposal in 1976 was revolutionary. What was the proposal in 1976 specifically? It's a public key crypto system. You could say it's revolutionary in the fact that it doesn't require 2 separate private keys, and it requires a public channel where only one key is known, and that is still computationally difficult, more difficult than many other private key systems, to actually break backwards. Alright, so yeah, before we get to the exercises, I'm gonna go quick run, grab some more coffee. So... Okay, wow, apparently my internet is very unstable, so apologies for anything that could be involved with that. Okay. Let's go back here. Let's get straight to as much work as we can. Also, wow, this is like really bad internet. Okay. Hopefully the VOD still records correctly, and I don't know if you can tell. Worst comes to worst, this doesn't work. I don't particularly mind losing out some reading about the cryptography stuff. Anyways, okay. So, encode IX love X math using the crypto system in example 7.1. So, let's first of all, so we first take IX love X math. So we also note that A equals 0, 0. Zero, 1 up to Z is equal to, let me double check, Z is going to be equal to, in this case, 25. It's 9, so I would be 0, 8. Three. Then 11. Oh gosh, I don't know how to count. Right, so 14 for O. Wait, let me just don't mind me opening up Google real quick to search. So Okay, apologies for the lack of talking for the past God knows how long. Turns out I forgot to unmute the whole time. So basically, oh God, I'm embarrassed. I'm moving on. We previously proved that the if statement, if GCD of determinant A of 26 is equal to 1, then Z mod 26, the matrix A, is invertible, and we actually proved this for any n, Z mod n. So now we need to prove the other direction. So we need to prove that if a matrix with entries in Z26 is invertible, then GCD of determinant A of 26 is equal to 1. So let's get started on that. So like, moving here. So we have that if we give our matrix A the matrix representation ABCD, or our transformation A the matrix representation, then we have that A, if it's invertible, then we have AD minus BC is not equal to 0. And that was actually what it was previously writing the details down, and this is like for a more general field. Because if AD minus BC is not equal to 0, it doesn't even matter what your C1 and C2 are. You can actually just multiply things out to get a 0 there. So this will always be true. So from there, what we have is that if AD minus BC is not equal to 0, remember we're talking about congruences. So AD minus BC is not congruent to 0 mod n, which means that AD minus BC okay, let me turn my stream volume down. My stream volume just came way up. Okay. So AD minus BC is equal to C1 plus n. C1n or K n plus R so we need to show that R is equal to 1. So AD minus BC minus R is equal to Kn. Wait, no. Oh, wait, actually, wait. What am I thinking? Yeah, it's actually trivial. Okay. Yeah, it's like literally just the statement that it is. I was being dumb. My apologies. My bad. Alright, so. Yeah, that's just like, for the determinant of A in G26 to be equal to 1 is like what it means for that determinant to not be equivalent to 0 mod 26. Okay. That was on me to not get. Okay. Given the matrix A equals 3, 2, 4, 3, use the encryption function f of p equals AP plus b to encode the message cryptology, where p is equal to 25 to the t. I'm too lazy for that. Okay. Encrypt the file. I don't want to encrypt all this stuff. Every person in the class. Yeah, with a lot of this, like, I'll just leave the exercises up here. The really interesting conceptual one was to prove that a 2x2 matrix with entries in Z mod n is invertible if and only if the greatest common divisor of determinant of A in 26 is equal to 1. That was actually the big thing that I cared about, because it was like purely theoretic. The rest of these are like just things you can encrypt and decrypt on your own, and it's much better to use computer assisted methods than to kind of force yourself to do this painful amount of like hand work computation. Because if you saw earlier when the stream was particularly unstable, doing the hand computations for these sucked. Okay. Anyways. And I'll read the rest of these, but these probably don't look that useful. And I mean, it's only 12:22. I can probably just start reading algebraic coding theory, which is like going to be way more interesting because there's a lot more theoretic stuff behind it. Cryptography, this is very much an introduction to cryptography-esque thing. So, okay. In the RSA crypto system, it is important to be able to find large prime numbers easily. Also, this crypto system is not secure if we can factor a composite number that is the product of two large primes. The solution to both these problems are quite easy. To find out if an A number n is prime or to factor n, we can use trial division. We simply divide n by d equals 2, 3, and on all the way up to the square root of n. Either a factorization will be obtained, or n is prime if no d divides n. The problem is that such a computation is prohibitively time-consuming if n is very large. A better algorithm for factoring odd positive integers is Fermat's factorization algorithm. A. Let n equal ab be an odd composite number. Prove that n can be written as the difference of two perfect squares. Or consequently, a positive odd integer can be factored exactly when we can find integers x and y, such that n equals x squared. Okay. So if n is... Yeah, I think we'll do these. These actually seem like fairly fun. So n equals ab is an odd composite number. So we have that equals 2k plus 1. N can be written as the difference of two perfect squares, x minus y, x plus y. So we want to find x and y such that x minus y, x plus y equals n. So let's worry about this. So I'm wondering if AB is equal to 2k plus 1. Oh, this is weird thinking about it. Okay. Alright, so if n equals AB and x minus y, so we have x minus y. Oh, we'll just write for now x squared plus x squared minus y squared is equal to AB is equal to 2k plus 1. So we have that x squared is equal to AB plus y squared equals 2k plus 1 plus y squared. Alright, so what does this tell us about what y must be? So 2k plus 1 plus y squared has to be a square number. I mean, let's think about this. It's like, for example, let's just work through some examples. So 3 equals 2 minus 1, 2 plus 1. We know that we'll have some even... Oh, wait, okay. So if it's odd, then these two factors need to be odd. right? Because if they're even, we're multiplying an even number by an even number. We get another even number. So we have that x minus y equals 2k prime plus 1. And x plus y is equal to 2q plus 1. This actually might be enough information to solve. So x minus y, x plus y is equal to 2k prime plus 1. We'll do p and q. We'll do p and q. Because they're nice. 2p plus 1 2q plus 1 is equal to 2k plus 1. So we get that 4pq plus 2p plus q plus 1 is equal to 2k plus 1. Oh, no, I meant to use the select tool. No. Okay. So we have this information right here. Let me double check that I actually did the factorization correctly, or I did the thing correctly, because otherwise I will not be happy. So we subtract 1 on both sides. So we get that 2pq plus p plus q equals k. So first, in solving for q, we have that, move that up. We have that p 2q plus 1 plus q is equal to k. So we simply solve and we find that p is equal to k minus q is equal to over 2q plus 1, right? So now we have this information. Which means that since we can solve this out now. Alright. P equals k minus q over 2q plus 1. With our definitions, we had that x minus y is equal to we replace this with p equals 2 k minus q 2k minus q over 2q plus 1 plus 1, and we have that x plus y is equal to 2q is equal to just, oh yeah, because we don't have to have a separate expression, we just have 2q plus 1, right? So when we factor this out, we're going to get x minus y, x plus y is equal to 2k minus q over 2q plus 1 plus 1 2q plus 1. We're going to horribly compress this really quickly. Meow. which when we factor this out will give us 2k minus q plus 2q plus 1. Oh wait, now how am I doing this? Wait, let me think. So we distributed that, now we distribute that. Plus 2k minus q over 2q plus 1. We add 1 to that. Plus 1. Which this is equal to 2k plus q plus 2 plus 2k minus q over 2q plus 1. 2q plus 1. So we have that. And now remember that x minus y, x plus y, we set it to originally be equal to this expression. So we can get rid of that equal sign. Is equal to AB is equal to is equal to AB is equal to 2k plus 1. Oh, okay, first I'm thinking we're not going to really need the AB in this. Maybe to prove it's an integer, but for now, we multiply everything by 2q plus 1 to get 4kq plus 2k plus 2q squared plus q plus 4q plus 1 4q plus 2 plus 2k minus q is equal to 4kq plus 2q plus 2k plus 1. So we have, let's just get rid of like terms. We get rid of the 4kq. We get rid of the 2k. And this brings us up to here, which says that 2q squared plus q plus, I should probably just write it out in full, plus 5q actually would be 4q because these q's cancel out. And then actually it would be plus 2 q's because also I'm going to get rid of this term and we divide that by 2. 2 q's plus 2k is equal to 1. Actually, no, we can just subtract the minus 1 on the side to get plus 1. So we have 2 q squared plus q plus k plus 1 is equal to 0. So actually, let me just write this out in full and use it as a quadratic polynomial with coefficients q is equal to 0. Implies that it's negative q plus or minus the square root of negative b plus or minus square root of b squared, so q squared minus 4 q squared plus 1 all over oh my gosh. Wait, what am I thinking? I'm being very dumb right now. Okay. So negative 1 plus or minus the square root of b squared. So 1 minus 4ac. So it'd be 8 because it'd be 2 times 4. And then it would be 2k plus 1 over 4. So it's showing that one of these has, I feel like I've gone a very out there way of doing this, and I feel like this isn't right. Let me go back to the chopping block. Alright, so x minus y equals 2p plus 1, and x plus y equals 2q plus 1. So we multiply 2 plus 1, 2q plus 1 to get 2k plus 1. So what we're going to do is we're going to solve for p, we're going to solve for q, and then once we have p and q solved for, we plug them back in to get equations with expressions in x and y. So this is 4pq plus 2p plus 2q plus 1 is equal to 2k plus 1. So we take off the 1s and we divide by 2 to get 2pq plus p plus q is equal to 2. I feel like wait, let me think. So this is the same as 2pq plus p plus q minus 2. I don't know, that wouldn't be able to give us something nice at least. So first of all, let's solve for p. When we try, actually wait. Okay. For now, we just keep this as a footnote. So we keep it as a footnote here. Now let's try to solve for this. So x minus y equals 2p plus 1. X plus y is equal to 2q plus 1. We get that x is minus 2p minus 1 is equal to y, and that y is equal to 2q plus 1 minus x. So we have that x minus 2p times 1, 2p minus 1 is equal to 2q plus 1 minus x. So we have that 2x is equal to 2p plus 2q plus 1 . Okay. Wait, I'm thinking something, right? So we have x minus y. Let me double check that my derivations so far are correct. So 2p plus 1, 2q plus 1. So we have that x minus y. We add y to that side. We subtract 2p plus 1 to get x equals 2p minus 1 equals y. And then y is equal to 2q plus 1 minus x. So we get that x minus 2p minus 1 is equal to 2q plus 1 minus x, which is equal to 2x plus 2p plus 2q plus 1. Alright, now something we can actually do then, if we want to simplify this slightly, is that we have p plus q is equal to 2 minus 2pq, which means that since this is equal to 2p plus q plus 1, this is going to be this will give us is equal to 2 minus pq plus 1. So 4 minus 2pq plus 1. Oh, whoa, okay. This actually might be kind of nice. So is equal to 3 minus 2pq. Now we take this and to just make this nice. So we have x solved for. So we have now that 2x minus 2y is equal to 2p is equal to 4p plus 1, 4p plus 2. So since we've solved for 2x, we replace it with 3 minus 2pq minus 2y is equal to 4p plus 2. So we add, we get that 1 is equal to 4p plus 2pq plus 2y. And then this is going to be really weird if I want to try to do something with that. No, not yet. So 1 equals 2 2p plus 2pq plus 2y. No. I'm getting lost in all these details. Wait, let me just like take a drink, take a step back, think more clearly about this. Okay. So let's run through some examples just to get a better idea. Before we worry about all this, I'll keep that up there. So we have 3 is equal to 2 minus 1, 2 plus 1. We have that 5 is going to be equal to 3 minus 2, 3 plus 2. We have that 7 is going to be an odd composite number. Four plus 3, 4 minus 3. So like, let's take the number 9 for example. 9 is going to be equal to 3 plus 3, so we take 4. Would it be 6? Wait. So an odd composite number, n equals 3 times 3. So we can factor it as... Wait, okay. Let me double check the restrictions of the problem. Alright, if it's an odd composite number, then it can be written as the difference of 2 perfect squares. So for example, 9 could be written as 416, so it'd have to be something actually a fair bit larger. Wait, what are the actual conditions on this? Let me think. Zero is allowed. 0 is allowed, okay. Zero. Okay, so let me think. So 0 is allowed, which makes a lot of our previous divisions mute. So if x minus y equals 2p plus 1 and x plus y equals 2q plus 1. Well, also, let's just note here that, like, we take this, right? And we just add these equations together to get x minus y plus xy to get 2x is equal to 2p plus 2q plus 2. Plus 2, right? 2p plus 2q plus 2. Or that x is just equal to p plus q plus 2. Or plus 1. So x minus y, well, let me double check that because that seems like a kind of powerful step. So 2p plus 2q plus 2, we get that x is equal to p plus q plus 1. So y is equal to, we just subtract it to get 2y is equal to 2q plus 1 minus 2p minus 1 to get is equal to 2q minus 2p, which implies that y is equal to p minus q. Alright, so we have these, right? We have, also let me double check that it actually works. Yeah, it looks like it works. It's like x minus y. So we take away the, wait a minute. No, this ain't right. Wait, let me double check that I did all the arithmetic correctly. So x minus y. X minus y. We're going to be going back to like middle school methods right here. 2p plus 1. X plus y is equal to 2q plus 1. So we get that 2x is equal to 2p plus 2q plus 2. Alright, so x is equal to p plus q plus 1. That much is like pretty much indisputable. Save that little factoid up there. Now we have that y plus x is equal to 2q plus 1. And we note here that y minus x is equal to negative 2p minus 1. I think I switched the p's and q's around previously, which gets us that 2y is equal to 2q minus 2p, or that y equals q minus p. Y equals q minus p. Let's double check that this is working correctly. So if we add x minus y, will give us the right values, yes. And then x plus y will also give us the right values. So, knowing this, can we solve for p and q is going to be the big question. Well, let's first of all check this. So we have p plus q plus 1. Oh, okay, we'll just give us our original identities. So now we have to use this information. All right, wait, let me think. Let's go back to what this is. If we have an odd composite number, that means that each of these must... I'm so dumb. So we have that a is equal to 2k prime plus 1 because it's odd, and b is equal to 2k prime plus 1. So we simply let x be equal to k prime plus k prime plus 1, and y is equal to k prime minus k prime, because it's the substitution for the p and q values. Oh, I feel dumb for not seeing that for a while, but at least I finally see it. And this fundamentally comes down to the fact that I literally had it set up right here. Oh my god, it took me way too long. It literally comes down to the fact that these must be odd because they multiply together to be an odd number. And if you multiply any odd number by an even number, it's an even number. So in order for this to be an odd integer, they must both be odd integers in the factorization. Alright, write a program. Nope. Okay. Primality testing. Recall Fermat's little theorem from chapter 6. Let p be prime with greatest common divisor of a and p equal to 1. Then a to the p minus 1 is congruent to 1 mod p. We can use Fermat's little theorem as a screening test for primes. For example, 15 cannot be a prime, since 2 to the 15 minus 1 equals 2 to the 14 congruent to 4 mod 15. However, 17 is a potential prime, since 2 to the 17 minus 1 is congruent to 2 to the 16 is congruent to 1 mod 17. We can say that an odd composite number n is a pseudoprime if 2 to the n minus 1 is congruent to 1 mod n. Which of the following numbers are primes and which are pseudoprimes? This is a question for a calculator, so we're going to worry about that. Okay. Pseudoprime n is a pseudoprime base b. Show that 3 4 numbers 2 but not a pseudoprime base a or prime all primes. There exist composite numbers that are pseudoprimes for all bases which they are relatively prime. These numbers are called Carmichael numbers. The first Carmichael number is 561 equals 3 times 11 times 17 and 92. There's an infinite number of Carmichael numbers. However, Carmichael numbers are very rare. There are only 2,163 Carmichael numbers less than 25 times 10 to the 9. For more sophisticated primality tests, see 1, 6, or 7. Alright, so this section was kind of cool. The cryptography was pain, but the Fermat stuff was kind of cool. And I also like this exercise a lot because it forced me to go back to linear algebra. We've been streaming for a while, but like this has been a really unsatisfying thing so far. And also chapter 9 is isomorphisms. So, okay. I might stop streaming for now and then like start streaming again in like 30 minutes or something so that I can like keep these in technically separate videos. So, for the sake of the YouTube audience, thanks for tuning in. Have a nice day.